We were looking at a problem with bases on Friday, and we had found the concentration of the hydroxide. But I want to remind us that we can kind of go through that whole set using our little flippy doodle. Okay, so we got down to X, and X we said was the concentration of the hydronium, not the hydronium, the hydroxide. Okay. But we should be able to get to the concentration of the hydronium, we should be able to get to the pH, and we should be able to get to the pOH. So from here, for me, the easiest thing is to go to the pOH, and that's what we talked about doing on Friday. So what if the question says, what is the pH? So first we would find pOH by doing negative log of that concentration. And the only reason it's pOH is because this number is the OH. All right, so that gives us the pOH. How do we find the pH from there? Talk about this on Friday. 14 minus the pOH, right? So if the pOH is the pOH is 1.96, the pH is 12.04. Right? Those two things just add up to 14. And we're going to do something similar with this in just a minute. So don't lose track of that idea. All right, what if I wanted to know the concentration of hydronium? So if I was starting, this is back at the same spot that we were before, we had the concentration of hydroxide and we were here. What if I wanted to go to hydronium? So I could go from the pH, or I could go from this. So remember that the hydronium concentration and the hydroxide concentration are connected by Kw. Kw is 10 to the minus 14. So I just take 10 to the minus 14 divided by that concentration, and that can get me there. What could I have done from the pH instead if I don't want to use this 10 to the minus 14 and have to remember another number? If I have the pH, what can I do? That's where you can do 10 to the negative pH, and then that will give you that concentration. Okay, so we should end up with the hydronium concentration of 9.1 times 10 to the minus 13. So I guarantee on your final, I will ask you a question. It might be at the end of an ICE problem like this, or it might just be like, here's a concentration, find the other three things. But you will have to do all four of those things on your final. All right, so if we went in this direction, you would be able to find pH by going through the hydronium and then the pH. All right, so we can find the pOH. We can find P of other things too. And one of the common things that's used particularly in biochemistry, for those of you that are thinking maybe you might do biomedical sciences or biochemistry as a major, this is real important. We can do pKa. Works the same way, negative log of the thing. So stick a P in front of it, it means negative log of that thing. So if I have a Ka that is a teeny tiny number, much like our concentrations have been teeny tiny numbers, then I'm just going to plug it in the same way I would with a pH. So pull out a calculator, see if you can do this. I highly recommend having your own calculator that you know how to use. There are people who can support this notion, because trying to use a different calculator on the final exam is a pain in the butt. All right, now based on what we said for the pH, if you don't have a calculator, you could probably still tell me what the first number is by looking at this. What's the first number of the pKa going to be? A 3. It's one less than that, okay? So if I do negative log of the pKa, I get 3.15. Okay. The larger the Ka, which means having a less negative exponent, the stronger the acid. Okay. So it's easier, I think, to look at the pKa, where I'm not trying to look at this tiny little superscript at the end of a number. I'm just looking at the number to tell which one is stronger. But I have to remember that works like pH does. The lower means stronger, whereas with pH, the lower means more concentrated. All right, so let's take a look at these. We have some pKa's here based on what I just said, with A being 1 and D being 4. Which of these is the strongest acid? Yeah, the pKa with the lowest number is going to be the strongest acid. Okay. All right. What if I don't have the pKa's? Well, I could plug them all in, but if I don't want to take the time to plug them all in, what I want to do is pay attention to the exponents on each of these things. Okay. So looking up here, remember that the less negative, the stronger, the more negative, the weaker. All right. So these are actually the same ones, but we can tell if this were the question because that's a 2 and these are 3s and this is a 7, that the 2 is going to be the strongest acid. That makes sense? Okay. I printed out this next thing and I forgot to get it off the printer. But okay, we've seen this picture before, though, where we have our strong acids at the top and our negligible acids at the bottom, and our strong bases at the bottom and our negligible bases at the top. And we said if we have a strong acid, then we have a negligible or neutral conjugate base. And if we have a weak acid, then we have a weak conjugate base. But we can also look at that relatively. So the stronger the acid, the weaker that conjugate base is going to be. So if I'm trying to compare which one is stronger among these bases, these negatively charged things, I'm going to say, okay, this, let's say F minus, is the conjugate of HF, which is pretty high up here. So if I compare F minus to, say, ammonia as a base, since this is the conjugate of a stronger acid, this is a weaker base than this one is. Okay, it's kind of two-step thinking. You need to get yourself turned around in there, but just one goes up, the other goes down. Okay. So this is where we're going to come back to the KW again. Okay, we can compare the Ka and the Kb. So remember, the Kb for the base is going to be if instead of taking this ion with an H out front, I have this ion with a sodium out front and dropped it in water, what's going to be the equilibrium constant of producing hydroxide? Okay. And so remember, smaller numbers on the Ks are going to be weaker. So we have a big number here, or a less negative exponent. So this is a weak but fairly strong among the weak ones acid. So that means this is a very weak base. So the V there is very weak. Okay, so 10 to the minus 13. And then as I go down here with these becoming more and more negative exponents, these are weaker bases or acids. So this is a very, very weak acid. Then its conjugate base becomes stronger and stronger. Okay, so we can do those. What I want you to pay attention to with the numbers, though, is look at adding together these exponents. Okay, so I've got -2 and -13. What is that? Yeah, I know, you all said it in your head, -15. Okay, -3 and -12. 15. -7 and -8. -15. -11 and -4. -15. They are all connected in a very similar way to hydroxide and hydronium. And the reason it's 15 instead of 14 is because we've got this other stuff out front. So basically, Ka times Kb for the conjugates is going to be Kw. Kw was that 10 to the minus 14. So if I am looking at something where I can find these in a table pretty easily, these, it's not like you can look those up pretty easily. You have to calculate them. But if I need it, all I have to do is say, well, the Kb is going to be 10 to the minus 14 divided by whatever the Ka was. Okay. So if I want to go between acids and bases, whether I'm doing it with the Ks or doing it with the ions, I'm doing 10 to the minus 14 divided by it. I just have to remember it has to be like K to K or ion to ion. I can't go like hydroxide to Ka. That doesn't work. I have to be sticking with the same type. Okay, so why does that work? Let's think about what Kw was. That came from this reaction, right? And so we said these, I'm sorry, no, this came from the autoionization of water. But this reaction is a basic, I'm sorry, not, I shouldn't say basic, a simple acid dissolved in water kind of thing. So we have our hydronium and we have our conjugate acid here. So it's just a generic acid, A, right? And so Ka is equal to this, right? We found that several times. Yes. If I take this and drop it in water, sodium A in water, then I'm going to create a base. And so I get this reaction, producing hydroxide. Okay, so that's my Kb reaction. Okay. So now I want to take Kb and multiply it by Ka. What's going to happen when I do that? Come on, goes. Here's my Ka. Here's my Kb. And notice that I have Ha on top and Ha on bottom. A minus on top and A minus on bottom. So I can cancel those things out, remembering my fraction rules. Okay, what's left over? Hydronium and hydroxide. And that's exactly what this was. That's why those two things are equal to one. Okay. Let's try calculating pKa. Plug in a couple of these, see what you get. If you don't have a calculator, well, first of all, remember your phone has a calculator. If you turn it sideways, it'll do the scientific calculator. Usually, I don't know all phones, but most phones do. But if you don't have a calculator, at least figure out what that first digit's going to be on each of these. All right, anybody got the first one? What do you got? That is what I got. 1.92. Everybody else get that? Excellent. All right, somebody else have the second one? 2.15. Anybody else get 2.15? All right. So what the next one, what is the first number of the next one? It's going to be a 6 because this is a 7 here. So we're going to drop one less than that, right? And now notice that as my pKa is getting larger, what's happening to the strength? It's getting weaker and weaker. So I got 6.36 on that one. Then from the previous slide, I split up these two. So this is the polyprotic, and so that's the deprotonated form of the other one, but the pKa of this fits in between the two. Okay, so I get 9.2 for hydrocyanic acid, and I get 10.32 for the bicarbonate. Now remember that while bicarbonate can act as an acid. So it has this pKa. It also can act as a base. So this is a weird one where if I were to actually put that in water, it wouldn't actually form the hydronium ions because it also has the reverse reaction that it can do where it can, instead of giving up the hydrogen, it can pick up the first hydrogen. So when we have polyprotics, we get weird things going on sometimes. Okay, I think that's the end of that one. All right, now I want to look at anhydrides. Okay, so hydration, that has to do with water. So an anhydride is something without water. And so basically this is the reverse of saying, if I add water to this, what do I get? So I can have acid anhydrides and base anhydrides. Non-metal oxides, so remember that's our green corner on our periodic table here. These guys, if they're oxygenated and I drop them in water, as a general rule, they're going to form an acid. So it's going to look something like this. Whatever that non-metal is, that's what E stands for, is just could be a nitrogen, could be a sulfur, or whatever. I'm going to add the water, and then I'm going to end up with 2 hydrogens and an extra oxygen on there. Now, that's going to depend on what the element is, because we know nitrogen doesn't really like to take on 2 hydrogens. There's some rules around that, so it's a little bit sketchy, but that's the basic idea. Okay, so if I have SO3, sulfur trioxide, and I add water to it, then I get H2SO4. And what is H2SO4? Sulfuric acid. Is that a strong acid? Yes, that's a strong acid. Okay. I could also have, is that not working? What's going on there? A nitrogen oxide. And so nitrogen doesn't actually have 2 hydrogens, so we end up with 2 molecules of HNO3. And so HNO3, what's going on here? Leave that the way it is. Okay. So then we end up with 2 molecules of nitric acid. Is nitric acid a strong acid? Yes, it's a strong acid. Okay, and then I could also do this with carbon dioxide, which gives me carbonic acid. So carbonic acid is actually important in several ways. This is what we find in things like Coca-Cola and seltzer water and, all of the fizzy drinks, champagnes, things like that. That all has the carbon dioxide in it. So that means anything that's carbonated is going to be acidic because it's got this acid in it. But it also means that as we increase the amount of carbon dioxide in our atmosphere, this gets dissolved in the majority of the planet being the oceans, gets dissolved in water. So you might sometimes hear the term ocean acidification. The pH of the ocean is dropping. Now, it's not actually acidic. The ocean tends to be a little bit above neutral, but it is less basic than it used to be. And that has implications for what things are going to dissolve, such as the seashells of animals and the environments that they can live in. Okay, on the flip side, if I have a metal oxide, like calcium oxide, and I add water to it, then I end up with a hydroxide. So hydroxide is a base, and so metal oxides are what we call base anhydrides. Okay? Okay, so what we're going to do is we're going to look at the carbonic acid as being a polyprotic acid. But we want to think about what happens when we have combinations of equilibria. So back in our equilibrium chapter, we said if I have a forward reaction and then I turn it around, then my Ka, or not my Ka, my K goes from being products over reactants to reactants over products. I have to flip that upside down. Okay? So when I reverse a reaction, I get the reciprocal. Well, I can also do things like adding together reactions. So let's say I have these two equilibrium reactions that I'm adding together. So in the first reaction, my K is going to be CD over AB. And my second reaction, my K is going to be F over CE. Okay. When I combine the two together, I'm going to get what canceled out? C. And what do we call those chemicals that appear and then disappear in steps in a reaction? Intermediates. So the intermediates disappear. Okay. So my overall reaction is going to look like this. And what I'm going to end up doing is multiplying K1 and K2 to get the overall K. Right, so that's going to look like products of reactants of each of those multiplied together. And notice how those C's, the intermediates, one is on top, one is on bottom. So since this is on top and this is on bottom, those will cancel. And then I'll just end up with the products of the overall reaction and the reactants of the overall reaction. Okay. So what that means is that if I have a polyprotic acid where I can lose one hydrogen and then I can lose the other hydrogen, and I have a Ka for each of those, if I want to know the Ka for the whole thing, losing both of the hydrogens, I just multiply those numbers together. Okay. Okay. So we did this symbolically, but we can do it numerically too. Okay. So the reason that we just multiply the numbers is because it works out mathematically like this. All right. So let's take a look at the example of the carbonic acid. Let's see. Oh, yeah, this is the carbonic acid. Okay, so the first reaction is losing the first hydrogen and forming bicarbonate, and it has this Ka. The second reaction is losing the second hydrogen and forming just carbonate, and it has this Ka. So both are going to happen, but the second one only happens a little because we're only forming a tiny amount of this bicarbonate in the water to begin with. So there's not a lot of that reactant. And this is a really small Ka, so it's going to favor that reactant anyway. Okay. So what if we asked ourselves, how much carbonate, CO3 2-, is going to be in this concentration? That's a pretty high concentration of carbonic acid just to be sitting around in water. What would we do? Well, we would want to find the K value. Okay, so we would take K is equal to Ka1 times Ka2. Apply those two Kas, we get this. That's our first step. So that tells us what is the equilibrium constant for all of this. Now we have a concentration and we have a K. What do you think is coming next? A rice table. Still see a couple people writing some things down, so I'll give you a second. Okay, when we do a rice table, we have the reaction at the top. What is our initial concentration going to be? It's going to be that concentration that they gave us in the problem. Okay, so initial concentration of the carbonic acid is 0.0024. I'll have water all grayed out because we're not worried about it. The initial concentrations of our products, we're just going to say is 0. Next line is change. What do we do for change? Nickels and dimes? No. X's. We do have a 2 here, so we're going to have to pay attention to that 2. But in this question, we're not being asked about the hydronium, so it's not going to worry us too much. And then our equilibrium line is combining those two. Okay. All right, so we have our K. We're going to set the K equal to products over reactants. So we're going to have 2x times x divided by this. Do you think this X is going to be teeny tiny? Oh yeah, look at this exponent here. That X is so negligible, nobody's. Okay. Now remember that because this has a 2 here, when we plug it into our equilibrium, this whole thing gets squared. Okay. All right. Then we'll multiply both sides by this. We've got 4 here we have to deal with, so you're going to have to divide by that 4. And then this isn't a square root, it's a cube root. And that's a little bit different on calculators. I had to figure out how to do it on these little ones because it's kind of weird. But you can always do it as a fraction, so you can do it to the power of 1/3. If you can't figure out how to do a cube root, just do it to the power of 1/3. Yeah. You got 10 to the negative 16th when you plugged it in?
On the last slide.
When I was making the slides, I figured out one of them was wrong and I fixed it, and I don't remember which was the correct one. We'll see. Whichever one it is, this is what I got for my answer. And that's pretty small compared to the other one. So the amount of carbonate ion is comparable to the amount of hydronium ion in water when you have that carbonic acid. And the reason that might be important, is because this tends to be pretty insoluble. So if you're creating carbonate, you might precipitate out your calcium, your iron, or whatever that happens to be. Okay, so we will take a look at another kind of combination equilibrium on Wednesday, and then we will look at titrations on Wednesday. All right.